Hello everyone, in this video you are going to learn about multiplicative and completely multiplicative functions from applied number theory. Before going to this topic, let us see some basic concepts. Then what is arithmetical function? Arithmetical function is a function defined from the positive integers to the real or complex variables. There are types of arithmetical function. One is Mobius function, identity function, ruler torsion function and unit function and many more. Identity function. Identity function is an arithmetical function denoted by capital I and it is defined as I of n is equal to integer part of 1 by n which is equal to 1 if n is equal to 1 or 0 if n is greater than 0 is called identity function. Then what is integer part? Integer part of a number appears before the decimal. For example, 1 by 2. 1 by 2 value is 0.5. Integer part of 1 by 2 is 0. Now we'll see the example of identity function. If n is equal to 2, then identity function of 2 is 0 because the integer part of 1 by 2 is 0. If n is equal to 10,000, then the integer part is 0. If n is equal to 1, then the integer part is equal to 1. For any value of n, if n is greater than 0, then the integer part is 0. If n is equal to 1 alone, the identity function of 1 is 1. Mobius function. Mobius function is an arithmetical function denoted by mu. If n is equal to 1, then mu of 1 is equal to 1. Then for n greater than 1, then n is defined as product of unique prime numbers. If powers of unique prime numbers is equal to 1, then the Mobius function is defined as minus 1 to the power of k if a1 and a2 and a3 prime powers is equal 0 if ai is greater than 1 for some I. We'll see some examples. Examples. If n is equal to 6, the prime factorization of 6 is 2 into 3, which are unique prime numbers. Then mu of n is nothing but 1. If n is equal to 2, the prime factorization is 2 into 1, where 1 is not a prime number. So it is mu of 2 is minus 1. If n is equal to 210, the prime factorization is 2 into 3 into 5 into 7. It is a 4 prime factors which are unique. Then the mu of n is 1. 4. It is a 2 square. So the mu of 4 is 0. Hope you have understood what is identity function and Mobius function. Now let us dive into our topic, that is multiplicative function. What is multiplicative function? A multiplicative function is also an arithmetical function defined for all natural numbers. A function is said to be multiplicative if it satisfies the property that is f of m into n, which is equal to f of m into f of n whenever GCD of m and n is equal to 1 or m and n are co-prime. Examples: identity function and Mobius function. Let us solve some examples. Examples of multiplicative function. Take identity function. Choose m is equal to 7 and n is equal to 4. Here 7 and 4 is equal to 1, which means the GCD of 7 and 4 is equal to 1. They are co-prime. The integer part of 1 by 7 is 0, which means the identity function of 7 is 0. I of 4 is also 0. Then the identity function of 7 into 4 is equal to 0. Therefore, it satisfies the property of multiplicative function, which is nothing but identity function of 7 into 4 is equal to identity function of 7 into identity function of 4. Now let us see another example for multiplicative function. Take a Mobius function. Choose m is equal to 7 and n is equal to 4. Here m and n are co-prime. So mu of 7 is equal to minus 1, which is Mobius function of 7 is minus 1 and mu of 4 is equal to 0 because the prime factorization of 4 is 2 square. So the Mobius function of 4 is equal to 0. Then the mu of 7 into 4 is equal to 0. Therefore, it satisfies the property of multiplicative function, that is mu of 7 into 4 is equal to mu of 7 into mu of 4. Now let us see what is completely multiplicative function. A completely multiplicative function is also an arithmetical function, and if it satisfies the property, that is f of mn is equal to f of m into f of n for all natural numbers m and n. Here m and n need not to be co-prime. Let us see one example. Take an identity function, choose m is equal to 4 and n is equal to 8. The identity function of 4 is equal to 0. The identity function of 8 is equal to 0, which means the integer part of 1 by 4 is 0. The integer part of 1 by 8 is also 0. Therefore, it satisfies the property of completely multiplicative function, that is I of 8 into 4 is equal to I of 8 into I of 4. Now let us see another example for completely multiplicative function. Take a Mobius function, choose m is equal to n is equal to 2. Here m and n need not to be co-prime. So the Mobius function of 2 is minus 1. Mu of 2 is minus 1. Then mu of 2 into 2 is equal to 0, which means the Mobius function of 4 is equal to 0. Therefore, it does not satisfy the property of completely multiplicative function. That is, mu of 2 into 2 is not equal to mu of 2 into mu of 2. Therefore, we can conclude that Mobius function is not a completely multiplicative function. Now let us solve a problem based on multiplicative and completely multiplicative function. Let f of n is equal to integer part of root n minus integer part of root of n minus 1. Prove that f is multiplicative but not completely multiplicative function. Firstly, we will prove that f of n is equal to 1 if n is a perfect square, otherwise 0. Then it will be easy to prove multiplicative and completely multiplicative functions. We know that if any number k with y square is less than or equal to k is less than y plus 1 the whole square, then the integer part of root k is equal to y. Let us call this equation as 1. How did this equation come up? It is through square root by estimation method. We can guess the square root of 5 will lie between 2 and 3. That is nothing but 2 square is less than or equal to root 5 less than 3 square. So the general format of square root by estimation method can be written as y square less than or equal to k less than y plus 1 the whole square. That's how we have got this equation. So moving forward, if n is greater than or equal to 1 and is a perfect square, that is nothing but if n is equal to x square, where x is strictly greater than 0, then the integer part of root n is equal to integer part of x square is nothing but x. Also we have x minus 1 the whole square, which is nothing but x square plus 1 minus 2x. This can be written as less than or equal to x square plus 1 minus 2. How can we replace minus 2x as x? We'll see the reason. So if x is greater than or equal to 1, obviously 2x will be greater than or equal to 2. When you multiply minus 1 on the both the side, minus 2x is always less than or equal to minus 2. So we substitute in the place of minus 2x as minus 2. So further simplification, we get x square minus 1. As minus 1 is less than 0, we'll get less than x square. From above, we get x square minus 1, which is nothing but less than x square as minus 1 is less than 0. Therefore, x minus 1 the whole square is less than or equal to x square minus 1 less than x square. Therefore, which implies that the integer part of root of x minus 1 is equal to x minus 1. Then we also have the integer part of root n is equal to x, and the integer part of root of n minus 1 is equal to x minus 1 from above. So, we'll substitute in the equation, that is integer part of root n minus the integer part of n minus 1, which is equal to x minus into x minus 1, which is equal to, we'll get 1. Let us see one example. If n is equal to 4, the integer part of 4 minus the integer part of root of 4 minus 1 is nothing but 1. Now let us prove otherwise condition. If n is greater than or equal to 1, then and it is not a perfect square, then we can tell that n is equal to x and x is strictly greater than 0. Then we can tell that the integer part of root n is equal to the integer part of root x is nothing but an integer part, that is we can say that as p. Therefore, the integer part of root n minus 1 is also an integer part, that is p. So, we can conclude that the integer part of root n minus the integer part of root of n minus 1 is equal to p minus p, which is nothing but 0. Let us see one example. So, for example, n is equal to 3. The root 3 means the integer part of root 3 is 1. The integer part of root 3 minus 1 is also 1. So we get 0. Now we have finished proving that f of n is equal to 1 if n is a perfect square and 0 otherwise. We have proved this condition. Let us name for our reference as A. And now it is very easy to prove f of n is a multiplicative and but not a completely multiplicative. Let us see the proof now. Now we will prove that f of n is a multiplicative, that is f of n is equal to f of m into f of n. If the GCD of mn is equal to 1, that is nothing but m and n are co-prime. Here we have two cases. Case 1, that is m and n are perfect square. So let us define the function. So f of mn is equal to the integer part of root of mn minus the integer part of root of mn minus 1. We have already proved the condition and named it as a. And since it is a perfect square, then we can conclude that f of mn is equal to 1. Now we will see f of m into f of n. So the f of m into f of n is defined as the integer part of m minus the integer part of root of m minus 1 into the integer part of root of n minus the integer part of root of n minus 1. This is the defined function. Now, since m and n are a perfect square by a above proof, that is, we have mentioned it as a, by that proof we can conclude that f of m into f of n is equal to 1. So, we'll see the second case now. Now, we will see case 2. That is nothing but m and n are not a perfect square. So, first we will define a function. So f of mn is equal to the integer part of root of mn minus the integer part of root of mn minus 1. How do we get 0? We have already proved in the property called a otherwise condition. Otherwise conditions say that if n is not a perfect square, we can substitute it as 0. So we have concluded that f of mn is equal to 0. Now we'll see f of m into f of n. We are going to use the same condition for this also. We'll define a function, then we are equated to 0. So we get 0 for this. Since m and n are not perfect square, but by using the condition we can tell that f of m n is equal to f of m into f of n is a multiplicative. The given function is a multiplicative function by case 1 and case 2, we could prove that if m and n are perfect square and if m and n are not a perfect square, in both the cases, we can prove that f of n is a multiplicative function. The given function is a multiplicative function. So we'll see what about completely multiplicative function. Now we will prove that f of n is not a completely multiplicative function by using a counter examples. Let us take m is equal to 20 and n is equal to 80, and we will put these values in a given defined function. That is, f of 20 is equal to the integer part of root 20 minus the integer part of root of 20 minus 1, which is nothing but 0. So we'll see the case of f of m into f of n. What happens? So f of 20 into 80 is equal to the integer part of root of 20 into 80 is nothing but 40 minus the integer part of root of 20 into 80 minus 1 is nothing but 39. We are going to get 1. Here we could see that we can observe that f of 20 into 80 is not equal to f of 20 into f of 80. So the given function is not a completely multiplicative function. Therefore, we can conclude that the given function is a multiplicative but not completely multiplicative function. Now we have proved that the given function is a multiplicative but not completely multiplicative function by using a main criteria, that is main property, that is f of n is equal to 1 if n is a perfect square, 0 otherwise. By using this property, we could easily prove that it is a multiplicative but not a completely multiplicative function. So if you have any doubts related to these problems, please post your comments in the comment box. Thank you.